Oh, there we go. Okay.
Hey, Steven, which one's the oldest? I'm going to get the black.
Let's go ahead and get started. Okay, warm ups. A wire has a current of 15 amps running in the positive K direction. What is the magnitude and direction of the magnetic field a distance of 15 centimeters to the right of the wire? Consider positive I to the right, positive J out of the board, and positive K upwards. So we have
One of us could hold it.
K,
Turn AC round.
I, and J is coming out of the board.
That's nice.
What?
What's going on?
Morgan, what did you
What's going on?
I didn't do anything.
Okay.
Why does everybody want to blame me first?
Because you're holding on the cord.
Alright, so the formula we're going to use
I didn't
is
pull it
the
out of
one
anything.
for
It's
magnetic
sitting
field
there.
of a wire. B
I swear.
equals mu naught over 2 pi times I over R. Okay, mu naught, 2 pi, I over R. Mu naught is a constant, 4 pi e negative 7. I is current, R is the distance from our wire. So here's our wire. By the way, what's the lowest I can...
You should totally video
What's the
ball.
lowest I can record here?
Hey, Stan, can I
About here. Here is the low limit. Okay, so here's my current of 15 amps. I want to know the magnetic field over here. B equals what? Okay, this is pretty much just plug and chug, right? What's that? Is that what you got? Okay, so mu naught is 4 pi e negative 7
Anything
over
like that.
2 pi
So it's basically
Does he have any stress
times
involved?
15, yeah, 2 e negative 7, times 15 over, 15 centimeters, point that. Why do I keep using 15?
I don't know.
Anyway, so what does it come out to be?
2 negative 5.
2e negative 5. What are the units?
Tesla.
Tesla is magnetic field, so there is Tesla. Tesla. Okay, so here's our magnitude. What's the direction?
into the blood.
Ah,
It goes that.
we're going to use right-hand rule. Thumb in the direction of current, fingers curl in the direction of the magnetic field. So, thumb in the direction of current, fingers curl in the magnetic field. So we're going into the board.
So
Now,
why is it that the only letter you didn't have was into the blood?
what?
IJK.
Well, positive J is out of the board, so what would it into the board be? Negative J. Okay, so if I were writing this out all the way, it would be negative 2e negative 5 J hat Teslas. Okay? That is a perfectly acceptable way of writing it.
Wait, where's hat come from?
Hat is just means it's a unit vector.
Oh.
It just points direction, doesn't change magnitude. Mhm.
There's random food.
Anybody have any questions? I know, that's been there for a disturbingly long period of time.
It's kind of disturbing.
I think it might be somebody from
I don't know.
lunch.
Doritos, those last for like years. So.
Yeah, those last for years, but the sandwich in there?
No, Scooby-Doo snacks and some cookies and sandwiches in there with like a couple of
Would you like a strawberry bonbon?
No,
One.
The rest of the lot.
I'm of yourself.
Hmm?
You're gonna
Anybody
give it
like
to me
the
like in
cookies?
front of them. Just make them jealous.
Sam, you just run across with your nose and then I'll chase you with my tennis racket.
Okay, am I good to
Don't
erase?
beat me up.
Yes. Oh, I erased my little marker. There.
Do you have
Don't
pink
go below
ones
there.
though?
Okay, two parallel superconducting wires, 19 centimeters apart, have currents 1,200 amps and 1,500 amps. How much force is necessary to keep these wires stationary? Okay, so we got a wire here, wire here. Doesn't say which way their currents are running, but it doesn't really matter. Just one way will be attractive, the other way will be repulsive. And 1200 amps, 1500 amps. Okay, 19 centimeters apart. Alright, so how do I do this?
How do you pick a wire?
We need
You
to
just
pick
pick a wire and you
Uh-huh.
put the force on it.
Right, so pick a wire, find the magnetic field from that wire, okay? Ooh, I missed, there's a missing piece of information.
Not how long the wire is.
Right, how long do you want these wires to be?
1 meter.
A meter?
20 meters.
Yeah.
So our wires are 1 meter long. Okay, nice little missing piece of information there. Okay, so let's find the magnetic field due to this guy. Why not? B equals 4 pi e negative 7 over 2 pi.
Can't they just do 2e-7?
Yeah, you can. It's just that mu naught shows up a lot of other places, so.
And why did they
use
keep
that.
them separated?
Huh?
The mu not over
I don't know.
the
Just because it looks pretty.
2 pi.
We're gonna use this wire here. So 1200 over 0.19. So what's the B field for this guy?
Well, wouldn't radius be half of 0.19?
No.
It's like oatmeal and what?
I start here and I go
Butterscotch.
that far away.
Okay, that's true.
So what's that B field?
Ziploc really does.
I might get food
Calculating.
poisoning for tomorrow. It's your fault.
Shit, man. I have a lot of important stuff going on
Loading.
tomorrow too. So. I have another PT test.
You got it?
To do, yeah.
Yeah.
This is pretty
Test
good,
run.
actually.
Yeah.
We got it.
0.00126.
Point double
Thank God you're in
what
this
is it?
class.
Me?
126?
No. Aaron, thank God you're in this class.
126. Tesla.
Like, you're willing to do work when
Is
you're
that right?
You're
Okay.
awesome.
Plug it in the
So-
calculator.
I know no one else wants to do it.
There's our magnetic field, okay? Now that's the magnetic field over here where this other wire is, so let's find the force on that wire. Force
Field
equals
sign.
ILB sine theta. Theta is going to be 90, so we can just ignore the sign. So I is going to be 1500. Length is 1 meter, and B is the field we just found, 0.0026. Thank you. 126. So what's our force?
About 1.89.
1.89
Yep.
newtons. 1.89 newtons.
Cool.
That's not very much, is it? Anybody have any questions?
Do you miss Camden?
What?
Do you miss Camden? Having Camden? Yes and no. No.
Let's see.
Are you recording now?
Yeah.
Yep.
Yes.
Oh, really?
Anybody have any questions about this stuff? Okay. All right. So today I would like to introduce the concept of flux. Flux. Not.
Flux pavilion.
Huh?
Have you ever heard of flux pavilion?
Clickety click. Okay.
I'm gonna look up that SQL.
So flux has a very scientific definition. Flux is the amount of stuff that goes through other stuff.
It's like a really technical definition.
Yep. Don't you know?
Is this like the actual big boy version?
Well, okay. The issue is the reason that definition is so vague and bad is because there are many different types of flux. Okay, there's like volume flux, like water flowing through a pipe. There's mass flux. There's light
How
flux.
can you use mass?
That's lux, huh?
How can you
Unpopular
mass?
thought.
The amount of
That
mass
was
going through a
back
given
then.
place. So like a mass flow rate could be considered flux. Well, kind of. They're defined a little bit different. There's electric flux, which we didn't look at, but APC did. And there is magnetic flux, which is what we're going to look at today. Okay? So we're looking at magnetic flux.
Will this be in C as well?
Yes.
Okay, I'll take notes.
Okay? So magnetic flux, represented by capital Greek letter phi. It is a cool one. Green Lantern.
And I with the circle.
Ooh. Okay? So, here are my magnetic field lines. Whee! Just like that. Magnetic field lines. Okay? So that's the first stuff. Now the other stuff is going to be an area, a cross-sectional area. So let's take our little sheet of paper here. Okay? And say it hits like that. Okay, so I have a little sheet of paper with area A. All right, magnetic field with strength B. Then the flux for this would just be A, B, C, D, E, F, G. Easy stuff, right? Let's kick it up a notch.
No.
First of all, let me look this up in our book to make sure I'm giving you the same variables that they use. I hate when they do that, when they change it up.
It's very annoying.
Yeah, they're using the same ones. Oh, they use BA. Oh.
I got a lot of
That's pretty BA, yeah.
Okay,
I got a lot
so.
of Velmas and my Scooby snacks. I got a
Okay.
You got too many go.
Let's kick it up a notch.
and a Shaggy.
Let's start
Red.
tilting this sheet of paper because I don't think this is the
As
full
seen on
definition. Okay, I don't believe
As
hard
seen on
enough.
TV.
Is it absent?
Huh?
Is it absent?
That's pretty
Absent.
Sort of.
It might be. Sine,
Supposed to prevent
theta,
people
cosine,
from
theta.
taking
We'll
their
see.
credit
We'll find
card.
out. Okay,
Things
so let's
that
start
like
tilting
put
this
those
piece of paper.
To your credit card.
So here's my magnetic field. Now I'm going to go to the extreme right off the bat. I'm going to tilt it until that sheet of paper lies
Morgan
flat.
Freeman.
Okay, so here's my sheet of paper.
Hmm?
Here's the magnetic field lines.
Somebody stole my wallet, that's why I got that.
How much
So I had to replace it.
how much magnetic field lineness goes through that sheet of paper now?
0.
None. None whatsoever.
Is it flat?
It's flat. Okay? The
Okay,
magnetic
well,
field
that-
lines, even if I draw more lines, you can see it just goes straight along the surface. It doesn't
Like
actually go
5
through
meters, I think.
the paper. Okay? So, this is not a
But I
complete
already got
definition.
graphic.
There is some dependence
like
on
separated the
angle.
field.
Alright? So what we
Just have to bring
need
cash to me,
What we need is some way to relate the orientation of a surface, okay, to angle. And we're going to do that with what's called a normal vector. Normal vector. What does normal mean? Does anybody remember?
Perpendicular.
Perpendicular to. Alright, so what I'm going to do is I'm going to have this little sheet of paper. Okay? And I'm going to have a vector sticking out of that paper. Alright? That is perpendicular to the surface. Just like that. Okay? This is our normal vector.
Is there an
Okay.
abnormal vector?
Was that?
Is there an abnormal vector?
No. There is a tangent vector. Actually, there are multiple tangent vectors, so you seldom see them used.
Are they parabolic at all?
No.
Okay.
Geometric.
Okay, so here's this normal vector. If I take this normal vector and I multiply it by the total area, I get something called an area vector, which is really, really weird to think about, okay? We have an area with direction. Yeah, we do. I can have area facing this way towards me, or I can have area facing that way, or that way, or that way, okay? You can actually have area with direction.
Where moon is.
My area study is so cute.
Okay, so area vector. All right. So looking at our example here, here's our magnetic field going this way. Here's the area, the area vector going that way. What's the angle between them? 90 degrees. Okay, 90 degrees. So when I have a 90-degree angle between my B field and my area vector, I get no flux. Okay? So 90 degrees gives you 0. When I have a 0-degree angle,
So it's
right?
photons.
Ah, probably so.
Is that some of it?
Sure.
Here's my B field here. Here's the normal vector like that, going straight along. Okay, that's a 0-degree angle. 0 degrees gives you maximum flux. So it is cosine. It is going to be cosine. Yes.
I concur.
That's your eraser.
Oh.
Okay? This right here is flux. Okay? AB cosine theta.
Isn't there a synthetic material called flux?
Yeah, well, the stuff you solder with
Yeah, that's what I'm thinking of.
doesn't have anything to do with this.
How many
Yeah.
flux do I have?
Okay, so I saw like an awesome like story on Ann's website,
Mhm.
and there was some researcher there, some like no, not researcher, but Professor Emeritus was able to use violins to construct a human voice.
That's the weirdest thing I've ever heard. That's really weird.
It wasn't like straight up talking; it was just different vowels, like
Huh.
Italian vowels, but it was pretty profound.
Yeah.
Because they found out that the makers of the violins had so many
It's like
different vocals,
oatmeal,
Huh.
like
which
butterscotch
produced a
chocolate chip.
distinctly different sound.
That's weird.
Chip.
Is my phone freaking out? No, it's fine.
Please continue.
Okay.
This is the best video ever.
All right. So here's a question: flux. Is it a scalar or a vector? What do you think?
Vector.
Scalar.
Scalar.
Yeah, it's two vectors.
It will be, well, okay, I'm multiplying two vectors here. Now there are two ways to multiply vectors, right? There's cross product, which gives you another, vector, or there's dot product. If you multiply two vectors by the dot product, you get a scalar. That's why dot product is sometimes called the scalar product.
No.
And cross product is sometimes
So
called
it's
the...
not just like
What?
A,
Oh my
B, it's
god.
Yeah,
A dot.
right. Another way to write this would be A dotted with B. So if A and B are completely in the same direction, you get maximum, just A times B. If they're in perpendicularness-tude, you have 0. Perpendicularness-tude. That's a word. Okay? So there it is. There's flux.
So
We're going to do special things with that tomorrow.
A is what again?
A is area.
Area.
It's the area of this little sheet of paper
Exposed.
times the normal vector. Normal vector has magnitude 1, so it's not going to affect the amount of area. All it's going to do is give it a direction. Does that make sense? Do you want to try one? Try one like this? Okay.
God, more controllers.
There's not much to do with flux. It's really quite easy.
Would you like to try one?
Sure.
So here's my
I only have two
sheet of paper. What dimensions do you want to give this sheet of paper? 2 by 4? 2. You can figure not on the scale. 2 meters by 4 meters.
Small one.
Yeah. Let's have our magnetic field going a little wonky. There's our B field at an angle of, what do you think?
Am I supposed to suck?
20? 20
30.
degrees?
Okay.
20 degrees. How strong do you want that magnetic field?
2 Tesla.
2.
That's really good.
5 Tesla.
Okay.
5 Tesla. We got
My
Oh, never mind. Time's up. See you guys tomorrow.
Bye, everybody.
Oh wait, no, I don't leave.